Penetration testing, or pen testing for short, is a direct assessment of the security of a complete software system. Its goal is to find evidence of insecurity, typically taking the form of exploitable vulnerabilities. Pen testing is a black hat activity done by so-called red teams or tiger teams and employed for the good purpose of finding security defects prior to deployment. What is the target of a penetration test? The focus can be any of several different levels of a system made up of executable components. We can fuzz test single programs, or we can look at complete applications like web applications, consisting of communicating programs, the browser and server. We can even look at entire networks, looking for weaknesses that cross application boundaries, where one system could be exploited to then take advantage of another. In all cases, we're looking at whole programs, not parts thereof, like code fragments or configuration files, libraries, and so on. Now, who are pen testers, and how do they work? Well, pen testers are teams that use guile and automated tools to find security issues. A good pen tester is creative, thinking carefully about how a system is put together to find assumptions that turn out to be weaknesses. Good tool support is essential for an effective pen testing engagement. As the pen tester comes up with hypotheses about potential weaknesses, tool support can be used to systematically probe a target and see if those weaknesses are present. Pen testing is carried out late in the development process by a team that is different from the one that built the system. Having a separate team ensures that the target is given a fresh look. Developers can have blind spots about their own software, and a separate team can help see past those. A separate team is also useful in that pen testing requires a specialized skill set, and this skill set can be developed across multiple projects. The pen testing team may be told a lot or a little about the system that they are testing, and given a lot or a little access to its deployment environment. We might, on the one hand, try to simulate the access that an attacker should have, for example, only from outside a company firewall via forward-facing components. On the other hand, we might provide more access or information to model an attack by a company insider. In general, giving an adversary more powers gives a better idea of how the system holds up if some defenses fail to hold. That said, if the design was against a weaker threat model than is being tested against, then it shouldn't be surprising that we'll find additional issues, and discovered issues should be assessed and kept in perspective. Pen testing has been around for quite a while. As computers were coming into wider use in the 1960s, time-sharing operating systems emerged, which allowed multiple users to use a computer at the same time. Previously, computers were largely used in batch mode, running one program at a time, which left no remnant behind. Time-sharing, with per-user storage, introduced new security challenges. In particular, operators were worried that one user might present a security risk to another user. As such, a task force of experts headed by Willis Ware of the RAND Corporation was formed to look at the issue. His team produced a report in 1967 that came to be known as the Ware Report. Many of the ideas that we have discussed in this class were first brought to light in the Ware Report. For example, the different categories of security policy, confidentiality, integrity, and so on. Relevant to our current discussion, the report also used the term penetration to describe a successful attack on a computer system. By the 1970s, the government was regularly using teams to assess the security of computer systems by trying to penetrate them. These teams were referred to as red teams or tiger teams. Today, penetration testing is a mature field, with services provided by independent companies, as well as divisions within larger organizations. Much of the buzz about cybersecurity, particularly among students, focuses around penetrations, which are gamified in CTF or capture the flag competitions, like DEF CON. There is also a penetration testing certification organized by the Information Assurance Certification Review Board, or IACRB. The certification is based on both conceptual material and a demonstration of skills by hacking into a target VM. Why should we do pen testing? Well, it has several benefits. First, penetrations are certain. After all, they have been demonstrated. Hopefully, they also come with some reusable evidence. For example, evidence of an SQL injection could be the exploit payload entered in a form field of a web application. As such, unlike errors produced by, say, code reviews or static analysis tools, penetrations are not hypothetical. By virtue of the fact that they are applied to whole deployable components, they're also relevant under realistic configurations. And just as they are not hypothetical, they're not wrong. Penetrations are not, or are rarely, false alarms. Pen testing has non-technical benefits as well. One of them is a feel-good factor. After completing an engagement, those responsible for the target system can feel like they have really improved security, or will soon once they fix the issues. And this is because they have found real vulnerabilities that probably would have gone unfixed and could really have been exploited in the wild. Before this point, such vulnerabilities were only hypothetical, not made manifest. Now, on the other hand, penetration testing is not a panacea. We have to be careful not to assume we're getting more out of it than we really are. Most importantly, penetration testing will not find all of a system's security problems. As such, an absence of any discoveries does not imply the absence of vulnerabilities. Likewise, fixing vulnerabilities that were found, if any, does not mean that none are left. Penetration testers may not even have looked for certain sorts of problems, depending on the rules of the engagement and the assumptions of the threat model. Security, to the extent that pen testing has established it, is ephemeral. We cannot rest on our laurels. When you change the software, the configuration, the network topology, and so on, you potentially create new vulnerabilities. Why? Well, an important thing to keep in mind is that security in general is not compositional. This observation was first made by Leslie Lamport, recent Turing Award winner, back in the 1970s. What it means is that two components that are secure on their own are not necessarily secure when used in combination. Penetration testing looks at the whole system, and that's its advantage. But subsequent changes might break a component and thus compromise the system. Even worse, a change to one component might not break that component, but could break the whole system anyway, due to the lack of compositionality. As such, we must employ the other processes discussed in this course to reduce the chances, as much as possible, that we break components. And we must employ whole system testing to ensure that the composition works too. In short, despite its limitations, penetration testing is something very much worth doing. Okay. In the remainder of this unit, we're going to consider two parts. First, we present an overview of pen testing and the tools that are commonly used by pen testers. We will see that pen testing is both art and science. As an art form, it relies on the creativity and ingenuity of the pen tester. As clearly successful techniques emerge, pen testing moves to becoming a science. And the fruits of this science are turned into tools and automation that subsequent pen testers can use. And we'll look at several tools in particular. First, Nmap is a tool for scanning networks, probing for computers and other devices that might be targets of attack. Zap, another tool we'll look at, is a web proxy that intercepts communications between a web browser and a web server, allowing the pen tester to see what's going on and to manipulate it, looking for vulnerabilities. Third, Metasploit is a tool for developing and deploying exploits. It is highly configurable with a toolkit that pen testers can use to find and exploit vulnerabilities. Now, in the second part of the unit, we'll consider fuzz testing, or fuzzing, a technique that many penetration testing tools employ. Fuzz testing works by corrupting inputs and interactions between target components. The goal is to see whether such corruptions will cause the system to break in a way that could be exploited in an attack. and we'll consider several tools and techniques that have proven to be successful. What is penetration testing? Penetration testing is the process of trying to find exploitable vulnerabilities in complete systems or system components. And it is both an art and a science. Pen testers must be creative. They must think about how a system is put together and poke it and probe it to see where assumptions made by designers represent weaknesses. Pen testers will cleverly adapt to what they find. As they gain a foothold in one place, they may use that foothold to exploit a weakness somewhere else. Over time, certain patterns of weaknesses emerge. Many systems will be incorrectly built or misconfigured in the same sort of ways. When patterns are discovered, we can build tools that systematically look for those patterns or try to exploit them. In a sense, this is ingenuity automated. As Donald Knuth once said, "Science is something we understand well enough to tell to a computer, while art is everything else."
A pen tester's job is to find vulnerabilities in the applications being penetration tested. What's in a pen tester's bag of tricks to make him successful at that job? Well, a penetration tester needs to approach a target knowing a lot about the target domain. For example, if the pen tester is attacking web applications, then the pen tester needs to know a lot about how the web works. You also need to know how systems are built in that domain. For example, what protocols allow applications to communicate. For the web, that's HTTP and TCP and IP. The languages that are used to build applications, like PHP, Java, or Ruby, if we're talking about the web. Or frameworks that are used to build applications or application components, like, for the web, Ruby on Rails, Dreamweaver, Drupal, and so on. You also want to know common weaknesses from that domain. For example, the bugs that are common to web applications, like SQL injections, or cross-site scripting, or cross-site request forgery. Or common misconfigurations or bad designs, like the use of default passwords or hidden files. Continuing our example of pen testing the web, consider one professional's point of view of what web hacking is about. 70% of the process is simply messing with parameters. So for example, if the target URL is the following, which you can imagine is what one might generate when clicking a button to buy an item on an online store, you could try to change the URL to change the price and see what happens, or change the item number to see if you can buy something else. This would demonstrate that client parameters are unwisely trusted by the web application. Or you could try to insert a script in the parameters that are sent in the URL. If this works, then maybe it's susceptible to cross-site scripting. Or you could add structural characters to the URL, for example, to see whether or not you can inject other sorts of code. Another 10% of web hacking might be default passwords. That is, research what the default password might be and try it out to see whether or not the target has changed it. This research could be through online searches or through looking at user manuals. Another 10% might be hidden files and directories. Again, you could look through manuals for clues, or you could just try out a bunch of common file names on the directory by typing in different URLs. You might find password files or other administrative pages. And the remaining 10% might be other things like authentication problems such as bypass or replay, or insecure web services, that is, ones that provide APIs that don't require any authentication, or a configuration page that gives away passwords.
Now let's talk about some pen testing tools. Pen testers use tools for a variety of tasks. They use them to probe the target system, to understand important characteristics about it. Pen testers also use tools to gather information about a system and perhaps test hypotheses about it. For example, they may see how it responds to certain sorts of stimulus. Finally, pen testers will use tools to actually exploit a target system, to demonstrate an actual vulnerability in it. Now, there are many possible security tools out there. Which should we use? Well, the answer depends on the target of our test and of our goal. If we're pen testing a network, then tools should explore the entire network, its components, its topology, and so on, looking for issues. If we're targeting a single machine, tools might help us figure out what files are on that machine, and what software it's running, and what exploits it's susceptible to. If the target of our pen test is a single program, then tools will help us to explore that program's attack surface, to see where it might handle input incorrectly, and as such be vulnerable to an attack.
The first tool we'll consider is Nmap, which is used for network probing. Nmap stands for Network Mapper, and it will figure out for you what hosts are available on the network, what services, that is, application name and version, those hosts are offering, what operating systems the hosts are running, and what type of packet filters or firewalls are in use, and many other things. Nmap works by sending raw IP packets into the network and observing the effects. You can give it a range of addresses, and it will send packets to those addresses, watching how the hosts that it tries to find at those addresses respond. Nmap is free open source, though there are commercial variants as well, and you can get it here at this URL, nmap.org. So in a little more detail, here's how Nmap might find hosts and services by sending pings to various IP addresses. In particular, it might send ICMP echo request or timestamp requests. These are the implementation of the standard ping protocol. Now, sometimes these packets are dropped by routers or firewalls, and so other packets should be injected as well. We might send TCP SYN or TCP SYN-ACK messages to ports 443 or ports 80. If we get any sort of response, that suggests that an HTTP or HTTPS server, that is, web servers, are running on these ports. Nmap will try other things as well as designated by the operator. That is, it might send UDP packets, that is, user datagram protocol packets, to particular ports, and it might fill out those packets to look like what's expected of packets on those ports. For example, DNS often uses UDP, where DNS is the domain name service, and we could send DNS packets to that port and see whether or not there is a domain name server running at a particular address. Nmap will also send probes to other TCP ports, for example, looking for web servers or other TCP-based services like FTP, and it will send probes that may elicit different responses on different operating systems in an attempt to fingerprint which machines it's talking to. Nmap can also attempt to be stealthy. A flurry of activity may be detected by an intrusion detection system, and so Nmap can be configured to emit packets at a slower rate to stay under the radar. Another common tool in a pen tester's arsenal is a web proxy. Web applications are common pen testing targets, and web proxies are useful because they sit between the browser and server, capturing packets. They'll display any packets that are exchanged and allow the pen tester to modify them. Some proxies have additional features for vulnerability scanning, exploitation, site probing, and so on. One example of a web proxy is ZAP, the OWASP Z attack proxy. It provides a GUI that the pen tester can use to inspect or modify captured packets. It can allow the pen tester to set breakpoints so that packets can go through quickly until a certain condition is met, at which point the exchange is stopped and the pen tester can have a look or make a modification. ZAP has several other features too, like active scanning, which will attempt cross-site scripting, SQL injection, and so on, fuzzing, in which the proxy sends context-specific payloads to see whether it can crash or otherwise corrupt the web application, and a spider that explores a site to construct a model of its structure, and this is useful to give a pen tester sort of a lay of the land of what the site is about and give him an idea of where to look for hidden URLs and things like that. ZAP is free and open source, but commercial tools are available as well, such as the Burp Suite. This is quite popular among professional testers. There is a free version of it, but the professional version actually doesn't cost that much more and provides many useful features. The third and final tool we'll consider that a pen tester may find useful is Metasploit. Metasploit is quite popular. It's an advanced open source platform for developing, testing, and using exploit code. It provides an extensible model through which payloads, encoders, no-op generators, and exploits can be integrated together. It works by allowing the pen tester to script attacks. These scripts take several steps. First, probe the remote site, looking for vulnerable services. Based on what's found, construct a payload. Encode the payload to avoid detection, for example, by introducing superfluous features that intrusion detection systems will be confused about and therefore fail to block. Inject the payload, and wait for shellcode to connect back. In the end, you'll have a command prompt that you can use post-exploitation. So here's how it works, visually depicted. On the left, we see the pen tester armed with Metasploit and some scripts, and on the right, we see the target network. 2 of the servers on the network are patched, but one of them is not. In step 1, Metasploit probes the vulnerable target systems, and maybe it's able to find the vulnerable server. Next, it constructs the attack payload, which it then sends along according to the script, triggering the vulnerability and compromising the target. In the best case, the target will connect back, providing the remote shell. The Metasploit framework has a bunch of different ways to support user interaction. For example, the MSF console is an interactive, type-based command prompt for executing Metasploit commands. There's also a web-based front end and a command line interface from the normal shell. All of these support probing and communication commands, payload construction and encoding, and support active and passive attacks. Active attacks are those that involve connecting to a remote service, while passive attacks are those that involve setting up a service and letting clients connect to you. Meterpreter is a command processor that's actually injected into the target, for example, in the memory of a compromised process. If someone on the target system were to look at the process table, they would not see that anything is amiss. They would see all the programs running that they expect to see running. Unknown to them, inside one of those programs is actually running a meterpreter, which is following the commands from the remote Metasploit operator. Obviously, this permits the pen tester to probe more stealthily. MSF payload and MSF encode are tools that generate stealthy shellcode. MSF payload generates the payload, MSF encode encodes it to make it hard to detect. Metasploit comes with hundreds of modules and script developed by a broad community over time. These include exploits against particular vulnerabilities, along with stagers and other modifiers that generalize the exploits to different platforms, tools for password sniffing, privilege escalation, and key logging and backdoors. All of these can be combined together using scripts to generate very sophisticated exploits. And there's much more. Kali is a Linux distribution with many open source pen testing tools installed and configured. These include the ones we have already mentioned, Nmap, Zap, Metasploit, and the Burp Suite, and dozens of other ones, such as John the Ripper for password cracking, Valgrind for dynamic binary analysis, Reaver for Wi-Fi password cracking, PeepDF for scanning PDF files for attack vectors, and many more. Overall, there are many pen testing tools that are available, all in different levels of use, and many of them are installed on this Kali distribution. As I mentioned earlier in this unit, sektools.org gives a comprehensive list. At this point, I want to make a note about ethical hacking. Penetration testing tools are meant to reveal security vulnerabilities so that they can be fixed, not so that they can be exploited in the wild for the purposes of crime or harm. But it is true that people will use these penetration testing tools for nefarious purposes. And that way, they are sort of two-way tools. Just as guns can be used to defend, guns can be used to attack. Don't be someone who uses pen testing tools to attack.
What is fuzz testing? Fuzz testing is basically a kind of random testing, which is a kind of testing in which inputs for a test case are generated randomly or semi-randomly. The goal of fuzz testing is to make sure that bad things don't happen. By bad things, I mean crashes, such as due to memory errors or uncaught exceptions, or hangs due to non-termination. As we have seen, memory errors often correspond to exploitable vulnerabilities, and thus are security critical. Non-termination is also a security problem since it can create a denial of service. Now, these are not the only bad things, of course. For example, a program could produce the wrong output. But a fuzz tester doesn't know anything about what the outputs of his tests should be. The fuzz testing tool only knows that those tests should not hang or crash. As such, fuzz testing is a very useful but a very limited endeavor. It complements but does not replace traditional functional testing. In fact, functional tests can be the starting point for fuzz tests. Input from functional tests is assumed to be legitimate, and fuzz tests can therefore derive input from these legitimate tests.
There are three basic kinds of fuzzing. The first is black box fuzzing. In this case, the testing tool knows nothing about the program or its input format, and instead just generates random inputs to throw at that program. Now, this is very easy to use and to get started using, but in the end, it may explore only shallow states in the program unless it gets very lucky. Grammar-based fuzzing works by having the tool generate input informed by a grammar that describes the input format expected by the target program. Now, this is more work to use because the operator needs to define the grammar, but on the other hand, it will often go deeper in the program state space. In particular, a grammar-based fuzzer will be able to get past the well-formedness checks that the target program probably is implementing on its input, and therefore will be able to cover more parts of the program. The last kind of fuzzer is a white box fuzzer. In this case, the tool generates new inputs at least partially informed by the code of the target program itself. Now, these tools are often easy to use because the fuzzing tool itself is able to look at the code and decide what inputs to generate to go to different parts of that target program's code. But as a result, they can be computationally expensive because they'll involve things like theorem provers. There are different ways that fuzzing tools generate inputs to pass to the target program. The most common way is by mutation. In this case, the fuzzer takes a legal input provided by the operator and mutates it using that as an input instead. Such legal inputs might be human-produced or automated, for example from a grammar or SMT solver query. The mutation might also be forced to adhere to a grammar. Legal inputs are often borrowed from legitimate functional tests. The second way that inputs are produced is generational. In this case, the tool generates an input from scratch. It might do so entirely randomly, or it might do so following a grammar to the program. And there may be combinations of these. For example, we could generate an initial input, then mutate it n times, generate new inputs, mutate those, and so on. And of course, mutations could be generated according to a grammar too. That is, if the original program's input adheres to a grammar, then we create mutations to that input that are informed by that grammar to make sure that it is likely to get further into the program's state space. Now, there are two basic ways that fuzzers are used. One is as file-based fuzzers, and the other is as network-based fuzzers. So let's look at the file-based approach. What's going to happen here is the fuzzing tool will mutate or generate inputs. It will then run the target program using those inputs and see what happens. So here it is visualized. An example of a file-based fuzzer is Redamsa. Another one is Blab. Redamsa is a mutation-based black box fuzzer. It mutates inputs that are given, passing them along to the target program. So here's an interaction with Redamsa. We start by echoing a legal input, passing it to Redamsa. Redamsa's arguments include a random seed, as well as the number of random input mutations to generate. You can see here that the inputs that Redamsa produced are variations of the input it originally received. Now, Redamsa can sit in between the generation of normal inputs and the receiving target program as follows. Here we're showing that the original input, which is a legal arithmetic expression that we might pass to the calculator program BC, can have that input fuzzed by Radamsa first before BC is able to operate on it. Blab is a grammar-based fuzzer. The grammars are specified by the user as regular expressions and context-free grammars. So as an example, Blab would take a regular expression as a command line argument describing the legal input space, and using that regular expression, it can generate an input that can be fed to the target program. Another example of a file-based fuzzer is American Fuzzy Lop. It is a mutation-based white box fuzzer, and it works according to the following process. We begin by instrumenting the target program to gather runtime information. This is how it uses the code to determine what the next inputs ought to be to improve coverage. The instrumentation it inserts tracks tuples that indicate where the program's execution has taken it, and these tuples consist of the ID of the current code location, you can think of this as just the line number, and an ID of the last code location before reaching the current one. With the instrumented program in hand, we run a test, and we mutate the test input to create a new test if an unseen tuple was generated by that test. Otherwise, the test was not useful for covering new spaces of the program, and we simply discard it. Mutations consist of things like bit flips, arithmetic, and other standard sorts of things used by mutation-based fuzzers. After running for a while, American Fuzzy Lop will periodically cull the gathered tests to avoid getting stuck in local minima. In a sense, it will stop making small local changes to tests and instead make one big change to try to jump to a different part of the state space. So here's an example interaction. We can start by running AFL GCC. This is meant to be a drop-in replacement for the GCC C compiler. AFL GCC will instrument the target and pass it along to GCC for compilation. Using the instrumented target program, we call AFL fuzz, and this starts the process of fuzz testing. This will run for a long time and produce diagnostics as it discovers failing tests. Another example of a white box fuzzer is Sage, and this uses symbolic execution as its underlying test generation technology. We talked about Sage in the prior unit on symbolic execution. Another kind of fuzzer is a network-based fuzzer. In one role, it can act as one half of a communicating pair, sending messages to and from a target program, trying to get it to crash. Inputs could be produced by replaying a previously recorded interaction and mutating it, or by producing an interaction from scratch, for example, from a protocol grammar. Here we can imagine the interaction specification being given to the fuzzer. The fuzzer can then interact with the target, mutating that interaction input until the target potentially crashes. Another role for a network-based fuzzer is to act as a man in the middle, mutating inputs exchanged between parties, again with those mutations possibly informed by a grammar. An example of a network-based fuzzer is Spike. Spike is a fuzzer creation kit, and it provides a C language API for programming fuzzers in C that interact with remote servers using network-based protocols. The way that a programmer uses Spike is to create a series of blocks that form parts of protocol messages and to leave holes in those blocks that Spike can fuzz. As an example, we might start off by specifying a size string call. This indicates that in the protocol, a length field for the rest of the packet will go here. We don't know what that length yet will be, so we leave a placeholder for it using size string. Next, we specify the start of the block whose length we're interested in, and we specify some contents of that block. If we want to insert constants, we can use the sstring call. Here we use the sstring variable call, where the argument is a prefix of the fuzzed component. So user equal Bob will be included in the block, and then a bunch of random text will follow it. We end the block, and this will determine the length, which can get backpatched at the start. Spike then allows you to connect to a particular host and port via TCP, send the block, and then close the connection. Of course, there are many other examples and interactions that Spike permits. Another example network fuzzer is Burp Intruder. It's one element of the Burp suite. Burp automates customized attacks against web applications, and it's similar to Spike in allowing the user to craft a template of a request but leave holes, which it calls payloads, for fuzzing by the tool. Unlike Spike, which is a programming API, Burp Intruder provides a nice GUI front end. And Burp Intruder integrates with the rest of the Burp suite, which includes a proxy, scanner, spider, and many other tools. Okay, so you've been penetration testing, you're using fuzzing, and a crash occurs. You have questions. For example, what is the root cause of the crash that the fuzzer found so that we can fix it? In order to figure this out, we might ask, is there a way to make the input smaller so that it's more understandable? Or are two or more crashes signaling what is effectively the same bug? That is, do they minimize to the same input so that when removing superfluous differences, they result in a crash? Some tools provide some assistance in answering these questions, for example, in trying to make the input smaller automatically. Sometimes, though, the operator needs to figure this out for himself. Another important question is whether a crash is security relevant. That is, does it signal the possibility of an exploitable vulnerability? Now, a crash due to dereferencing a null pointer is rarely exploitable, particularly when running a user space program, but buffer overruns more often can be. Memory errors are particularly difficult to deal with after fuzzing because the effects of a memory error may occur well after the point at which it originally takes place. That is, if you overrun a buffer and scribble over some portion of memory, the program will not immediately crash. Only when that scribbled over memory is reused will the program go the wrong way. One way to make it so that crashes happen immediately upon overwriting buffers is to use Address Sanitizer. This is a tool that can instrument a program so that accesses to arrays check for overflows and use after free errors. Given your instrumented program, you can fuzz it, and if the program crashes with an ASAN signaled error, then you can start worrying about exploitability. You can do the same trick with other sorts of error checkers for the purposes of testing. For example, Valgrind memcheck is another way of looking for memory errors. We've discussed several example fuzzers so far and the basics of fuzzing overall, and there are yet more fuzzers that are available for use. For example, the CERT Basic Fuzzing Framework, or BFF, based in part on an earlier fuzzer, ZZUF, is freely available, and it has been used to find bugs in commonly used software like Adobe Reader, Flash Player, Apple's Preview and QuickTime, and many others. Sully is a fuzzing tool that provides lots of extras to manage the fuzzing process. In addition to the core technology of generating random inputs to find useful test cases, Sully will watch the network and methodically maintain records about what's happened, instrument and monitor the health of the target, capable of reverting to a known good state if things go awry, detecting, tracking, and categorizing detected faults, and even fuzzing in parallel if that's desired.
Let's summarize. Penetration testing aims to simulate deployment scenarios involving determined attackers. The goal is to see whether the penetration team can find exploitable vulnerabilities. If they can, they have provided evidence of true insecurity. On the other hand, the lack of penetrations is not evidence of their impossibility, and as such, designs should always aim to mitigate and recover from as yet unknown attacks. Pen testers employ a variety of tools in their work, ranging from scanners to proxies to exploit injection and management tools to fuzz testing tools. Nevertheless, tools are no replacement for an ingenious and thoughtful testing person. Such a tester will use tools to increase the coverage, speed, reliability, and repeatability of her efforts. I'm very pleased to have with me today Eric Ames. He is a penetration tester at a company called FusionX, and we're going to talk to him today about what he does at FusionX and about penetration testing. So, Eric, welcome.
Thank you.
So, tell us how did you get involved in computer security, and maybe you can say a bit more about your background.
Okay. So in school, I majored in computer engineering, computer science, like program, focusing on development. I thought I wanted to be a developer. I worked for a couple of years on a large-scale software project with about 30 other developers and decided that doing that full-time was not necessarily for me. And so I had an opportunity to get involved as a junior security guy with another company, and I was the low man on the totem pole. So they called me the virus boy. I was kind of the guy that responded to virus incidents, and I did that for a little while. And at the same job, they needed someone to look at the security of the printers. That was sort of a low man on the totem pole kind of job. So I started my career penetration testing printers, and what can you do with a printer. And so after playing with it a while, I was man in the middling my printers and bringing up people's documents on my screen and things like that. So that's kind of where I got into the field a little bit. And then the next job, subsequent jobs got me a little bit closer and closer to what I wanted to do.
So now you work at FusionX. Maybe you can tell us a little bit about what the company does and what you do in particular at the company.
Okay. So FusionX specializes in penetration testing. Really, my bosses don't even necessarily like the words penetration testing right now because they feel like it's perhaps a little bit watered down. There's no real universal agreement on what standard a penetration test has to meet. So they would probably call themselves cyber security exercise or cyber security assessment or something like that. But it's the basic idea of a penetration test where we go in and we're simulating an advanced adversary trying to do whatever an advanced adversary would want to do to their organization. Could be stealing personal information or financial secrets or company sensitive information of some kind. And then me, I'm one of the penetration testers in that company, so I will travel sometimes I'll work remotely, but a lot of times I'm working on trying to break into an enterprise in some way. Could be through spear phishing or applications vulnerabilities or network vulnerabilities, but I'm trying to break in, and then once I'm in, pivot to find something that an attacker would want to find.
Got it. So maybe you can say a bit more about the steps involved in a penetration testing engagement, right? Your company provides this service, so then another company comes along and says, hey, we'd like you guys to come do a penetration test, say, on our network running various applications. What are the steps of performing that penetration test? What do you do?
I think the first step is probably just agreeing on the scope of the test. Trust is so important because they're basically hiring you to break into their network, and if they can't trust you, you're not going to get anywhere. So I think settling on a scope and rules of engagement would probably be the first step. Once we get into the technical part of it, I would say reconnaissance, trying to figure out where your targets are. A lot of companies, especially big companies, don't even necessarily know everywhere that they're on the internet. So part of it, before you even start, really is finding out where they are and getting kind of the lay of the land. Then I would say kind of comes a enumeration / scanning phase, exploitation phase, and I would say those two are not necessarily I do all of the enumeration and then all of the exploitation. I think if I find a vulnerability, I'll go with that vulnerability and see where it takes me. So I probably would do enumeration, exploitation, what I would call probably exfiltration, once I compromise a machine, getting all the valuable information off of that machine that could help me then to pivot to somewhere else. So it could be maybe I've gotten passwords off of a machine, I want to reuse those passwords somewhere else. So I would say those phases, enumeration, exploitation, exfiltration, and pivoting, kind of come in chunks, and then I repeat that process until I have the goodies that I want or the assessment ends. And then I'd say it finishes off with reporting.
So in those different phases that you discussed, I imagine a bunch of it is manual sorts of stuff where you're typing stuff into website consoles, you're trying out to see whether they might be vulnerable to cross-site scripting or directory traversal or something like that. But I imagine other parts of it involve automation and tools. So I wonder if you could tell us a bit about the tools that you use and maybe the higher level techniques that you employ when you out your penetration tests.
Okay. So we try not to do too much automated scanning, but we do have a bunch of tools that we like. Part of what we try to do is when we're simulating an adversary, we don't necessarily want to rush in there with Nessus or another noisy vulnerability scanner because that can give you away very quickly. And part of what we want to test is how far can we get before we get detected by their IDS or whatever kind of defenses that they have. So we like to do more surgical, manual type of testing. That said, I love doing web application penetration tests. I love Burp Suite. It's probably my favorite tool for that. Zap also works well. I like Burp Suite a little better, but Zap is nice.
Is Burp Suite, remind me, is that open source or is there only professional versions of that?
There is a free version that is limited, but the professional version is relatively cheap. I believe it's in the range of $200 a year or something like that. So for a company, it's not much. For an individual, it might be a bit much. But that's probably the professional version of Burp Suite is probably my favorite tool. Otherwise, Zap. And a lot of manual testing. We talked about Bad Store before. That's a great example where you can go through and manually, one at a time, and usually this gets well under people's radar, try out SQL injection and cross-site scripting and command injection and attacks like that. I also like Metasploit, not so much for the automated exploit packages like buffer overflows. I feel like in Metasploit are maybe not as useful as they once were. They're not as up to date. People don't share their exploits as much as they used to. I like the auxiliary modules though. There's a lot of good auxiliary modules that will help. Gosh, I can't think of any right now. But there's a million of those that I like to use a lot. So I'd say those are common tools. Oh, Nmap I use all the time. We try to scale back Nmap so as not to be detected. So we won't throw it at 1,000 ports at once or 65,000 ports at once. We might throw it at 10 ports that we know, 2 seconds between packets, just to see very slowly and stealthily what's on a network.
You bring up an interesting point, which is sort of the difference between a penetration test that is really completely and totally simulating an adversary and a penetration test that maybe is not so worried about stealth and is more brute forcing a system to try to see whether it's going to fall over and be susceptible to certain sort of vulnerability. So I could imagine, for example, a developer of a web application might use something like Nessus, which you mentioned, to see whether or not their site would be susceptible, and that would be great. And then later, when a corporation or whatever is trying to assess their overall posture with all of their different, you have an IDS system, like you said, you have host firewalls, you have printers, whatever. You want to see how does the entire network stand up, and that includes detection. So you have to worry about being stealthy.
That's a good point. Once in a while, we'll get to a customer that just is completely overwhelmed and they have no idea what's going on in their own network. And for a customer like that, we will recommend. We try not to give brand names, but Nessus is as good as any. Where it's a good starting point. If you run Nessus and you have 50 critical vulnerabilities, you're probably not even ready for a penetration test yet. It's something that a company can or an organization can buy on their own and run on their own and just cover the basics. And once Nessus comes back fairly clean, then maybe it's time to think about a penetration test. But up until that point, you're going to get so many results. It's not going to be as valuable to you, I would think.
So I wonder if you can tell us about some of the more common mistakes that get found during penetration tests, and maybe some of the more infrequent mistakes that you tend to find.
Sure. Default passwords, very, very common. It happens all the time. I find a lot of open shares, SMB shares, NFS shares, web servers that serve up sensitive information, FTP, anonymous FTP servers that serve up sensitive information. And by that, I usually mean passwords, maybe private encryption keys. SQL injection is very common. Cross-site scripting is very common. And then going a level deeper, maybe a flat network. I did a penetration test once at a hotel where I sit down at the concierge desk and plug in. And I was at the hotel's main domain controller. It was all connected together. So by being on the office area of one hotel, I could get to the same as our intercorporate network where all their sensitive information is. That's an example of a flat network. So it's just a whole design problem. That's very common. Or maybe just reusing passwords so extensively that if you get the admin password on one machine, you've got the admin password for every machine in the whole organization. Those would be all common ones. Less common.
It's interesting. I'm sorry to interrupt.
Sure.
How many of the things that you listed are not sort of application level vulnerabilities? There are the ways that people use their applications by, as you were saying, using poor passwords or organizing their site so that maybe URLs could be guessed and secret information could be taken out because they haven't put, say, a web access control policy in and they're relying on what they thought was secrecy that wasn't really there. Is that accurate? Is a lot of stuff really can be fixed with configuration rather than, say, software upgrades or changing software itself?
You're right. I focused mostly on network and not on software-specific vulnerabilities. I think those are the things that allow us to pivot from one to another more easily. I think getting that initial foothold is probably the hardest part of any penetration test. Getting that first level of access where you have something that you can then turn around and go somewhere else. And a lot of those are software vulnerabilities. Maybe cross-site scripting. I'd say SQL injection more often. Command injection is great when you can get it. Directory traversal. Maybe you could upload a web backdoor and get a shell that way. So I'd say the application level vulnerabilities sort of get me in the door, and maybe these configuration network vulnerabilities allow me to go from that level to the next level.
Before you get to the infrequent ones, another thing I observed in what you were saying before with the hotel example that you were able to plug into the network. One of the things we talk about in the course is having a threat model where you think carefully about what you think your adversary can do. And I think a mistake that people make, and maybe you can tell me what you think about this, is that they don't explicitly consider who their adversary is. They don't think that the adversary has this capability or this capability. I wonder to what extent, say, a hotel thinks that, well, anybody could plug into your network, and if they do, what sort of capabilities will they have? Are they still protected? Whereas if they had thought more carefully about who their potential adversaries were and maybe the risk of those potential adversaries, they might have done more to protect themselves.
Yeah, and this gets into sort of the human causes of vulnerabilities. I mean, I think there's a temptation to look at it as all technical. And that this problem, we fix these problems, then everything is solved and we're all happy. But there's always a human cause. And a lot of times there is, sometimes it's ego that no one could ever hack into our system because it's so great. And sometimes it's ignorance of, well, we don't necessarily have anything that an adversary would want. Why would they want to attack us? We're just this small company. But every company has something. Every company's CEO probably has some email he doesn't want on the front page of the paper. Everybody's got something, or even if it's just the horsepower of your machines, you have something to offer an adversary. So I think there is that is a very frequent thing we run across, that people underestimate what they have to offer a criminal, and then also overestimate their own defenses. And so one thing that we, as a penetration tester, we try to go in to do is a little bit is shock and awe. We try to go in there and get them spun on their heels and get their head spinning so fast after a couple of weeks that they're ready to sign us for more work. And it's I don't think it's unique to our company. I think it's every penetration testing company kind of likes to do that. So then hopefully their eyes open up and say, wow, we need more help. It's more business for us, and also it's good for them in the long run, because then now they're aware of problems that they had ignored before.
One thing that that occurs to me is that while I imagine big companies have their own penetration testing teams. You know, I'm sure Google has in-house folks, security folks that are doing penetration testing. Maybe smaller companies can't afford it, but that bigger companies might nevertheless benefit by having an outside group come in because they don't have the same blinders on, and they don't have the same biases due to the corporate culture that an outside group might have, and they might come at the problem a little differently and therefore find things that the company itself just was unable to see.
Yeah, I've been in both situations, working for a small company now, or working as a very small unit of a large company before. And in my experience, it's not even, if you're that guy that working for a large company, it's not even that you don't want to find the large vulnerabilities, or maybe you're not even that you're not able to. It's, I feel like as an outsider, you maybe get a little more respect and a little more freedom.
Mm.
Whereas if you work for the organization, oh yeah, you're always complaining. It's not that bad. And I think your comments maybe get a little more swept under the rug if you work for that company, or there's other political competing interests that maybe have a louder voice than you do. Whereas I think if you come in from the outside and you get buy-in at a high enough level within their organization, if you get buy-in from an executive level, then those guys, the executives, can say they're going to do the test, and you're not going to put these artificial restrictions on them, and we're going to find out what we find out, because we want to know the real deal. That is a very common thing I've seen in my career, where you're maybe doing a penetration test for some middle manager who doesn't want to look bad, and so he will artificially limit your scope, and the results are not realistic. So I think as a pen tester, one of your jobs when you set that rules of engagement and try to set that scope in the beginning, it's in everybody's interest if you push a little harder, because you don't want to get to the end and have an artificially limited scope, and then you don't find very much, and everybody thinks the whole thing was a waste of time, and nobody's happy. So what you want to do is you really want to push them in that direction in the very beginning, saying, look, we really want, it's important that we simulate a real scenario. So we don't want to be dismissed later on when they say, well, that wasn't realistic to start with.
And you certainly, you guys, neither you nor the customer wants to be in a position where the penetration test was successful, but then later on an adversary is able to penetrate because you were not unable to, you were not allowed to find the thing, the way in that the adversary chose.
Sure. Exactly.
So let's go back. I interrupted you before. Maybe you could talk about some of the maybe surprising or unusual things that you found during penetration testing engagements.
Okay. You know, one example I thought of was that, you know, one time I was just opening up a listener on my, I had a, it was an internal network penetration test, and I connected my laptop to the internal network, and I had a listener, I think it was for a part of a Metasploit exploit I was running, and so I had a port listening, I think port 443, and arbitrarily a host on their internal network connected to me and tried to authenticate to my server with domain administrator credentials. So just by listening, he connected to me and gave me the password of the domain administrator, which was, you know, made things very easy for me. I like it when, as a pen tester, I like it when they connect to me and just give me their password without me asking for it. So that was unusual. I was going to say before, I kind of alluded to this a little bit, I think the age of buffer overflows from Metasploit that are point and click and get you admin access, those days are going away. And it's pretty rare that scenario comes up now where I run into a device and there's a perfect exploit for it, either a Metasploit or somewhere else already coded for me and all ready to work. We don't do a lot of that. I think that was more 10 years ago, and now it's a little more manual testing and configuration problems.
Okay. I wonder if you could say a little bit, maybe from your experience or from those you work with, about what else, aside from penetration testing, security-conscious organizations do to make the security of their systems better. You know, if you go to a penetration test and the company that you're testing actually does a good job.
Hmm.
Do you know anything about what did they do to create such a secure network?
Sure. Um, I think what you do is you plan defense in depth. You plan for a situation where someone in your organization is going to click on an email link that they shouldn't have. You're not going to be able to get everyone to not fall for a phishing scam. Someone's going to click on it. So one user will get compromised, then what? Does that user's workstation, for example, have the same password, local administrator password, as every other user workstation or every other server even? So that kind of thing, the flat network thing that I alluded to before, how good is network segmentation? If one person's, say an employee at a bank clicks on an email, is that on the same network as their ATMs or customer account numbers, for example? So I think it's planning your network in such a way that one compromise doesn't mean game over for your whole organization.
Got it. I wonder if you could say a little about what you perceive to be, and maybe this is related to the limitations of penetration testing. Um, what should companies expect to get out of it, and what maybe shouldn't they expect to get out of it, and therefore they need to look elsewhere?
Okay. Limitations, I think a penetration test is usually not, in fact, it's never going to be an exhaustive catalog of all vulnerabilities on your network. Uh, they're they're limited by time and money and how much the customer wants to spend. So you're going to find a representative subset of vulnerabilities. You're not going to find all vulnerabilities. But if you kind of look at the root causes of these vulnerabilities, say you find 5 instances of default passwords. That's probably not every instance of default password on their entire network, but there's a problem of process. Why were these devices deployed with default passwords in the first place? Why is there some kind of process or testing or something that they can do to ensure this doesn't keep happening over and over again? Because even if they fix those 5, if 5 new ones are deployed next year, you're in the same boat. So yeah, the limit is you're not going to find everything, and you can't. I don't know any penetration testing company that gives companies their customers a guarantee, where once we pen test you, you'll never get hacked again. It would be.
I would, I mean, I would think
It would be a very good business model.
I would think that such a guarantee would be predicated on nothing about the network ever changing again, which would be violated the next day, right?
Sure.
Because the moment you stick a new printer on the network or you install a new software module, I mean, you might have introduced a new vulnerability, and that's something the penetration testing team could not have found.
Right.
I wonder if you can say a little bit about undergraduate education and advanced training. I mean, you mentioned your background was as a developer, and then you sort of, after your schooling, learned these skills sort of on the job and grew in your expertise. Do you think that that path was fine and everyone should take it, or should undergraduate and graduate education or maybe training do more to support penetration testing as an industry?
Uh, when I was in school, there was no penetration testing class. It wasn't an option. Maybe I would have gone a different way had that been an option, or if I had even. It wasn't honestly even on my radar at that point in my life. I think it's great that it's starting to come up more and more. I think it's very helpful. I think, but it's going to be based. A student's ability to get a job in the field is really going to be based on how much they've individually learned from it. I think I've been in roles before where I've been involved in. I was the lead at my last company for the penetration testing team, so I was involved in hiring decisions, and we didn't see a lot of people with undergraduate focuses in penetration testing. I still think a lot of colleges are catching up by adding that to the curriculum, but we saw a lot of certifications like CEH and CISSP and things like that. And I found that I really wasn't, at least speaking for the certifications, I really wasn't that impressed with people that had them. A lot of them are multiple choice tests, and people who pass them have not necessarily ever even used Nmap. They just passed the multiple choice test about it. And I think putting my hiring hat on, I would be very interested to talk to somebody who had a degree in penetration testing. That would definitely get them the interview and get them in the door. But then they would still have to convince me that they 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 retain the material, they know it, they use it, they're familiar with it. I think every penetration testing manager has something, whether it's some kind of written test or technical interview or hands-on exercise. We've all got something, because there's no that we've seen. There's no golden standard that when everyone has this certification, that means they're golden and they're qualified.
I mean, I would worry, frankly, that just like any other aspect of computer science and technology, that such a standard, if you had it, would be invalid in just a few years' time, right? I mean, if you look at the rise of the web, or you were even just mentioning sort of this shift from away from buffer overflows. I mean, I think in general people are much better about patching these days. A lot of the culprits of buffer overflows are getting those patches out faster. And so we've moved away from that as a problem, and now these new sorts of problems with web-based vulnerabilities, with mobile devices are coming up. So my impression, I'm just thinking about this course that we're offering on software security. A lot of it is about how does computing work? How does the network? How does the web work? And where are these strange interactions? Where are there opportunities to make mistakes that attackers can exploit? So if you want to be a good pen tester, you have to really understand how people built things a certain way so that you can take advantage of the mistakes that they commonly make, is my own impression.
Agreed.
Okay, fantastic. Okay, so I guess just one last question, which is, having worked in this field for quite a while, in penetration testing and in computer security generally, how have things changed over time? Like you said, 10 years ago it was one thing, now it's something else. If you look over that arc of the past 10 years, and maybe you look ahead to the next 5, how do you see things changing as far as computer security goes?
10 years ago I thought I was in the golden age of hacking, and then it just only gotten blown up more and more and more since then. I wish I could paint a idealistic future where security is solved. I personally don't feel that's the case. I think I kind of got to this a little bit before, but I think there are human reasons why security is a problem. It's not just technical reasons. There's ego, there's fear of looking bad, there's ignorance of the problem, there's not wanting to hear bad news. Sometimes it's political problems within the organization. Maybe the Chief Information Security Officer reports to the CIO, and the CIO's primary objective is just keeping everything running, keeping everything smooth, and he doesn't want to hear the problems. They don't get reported up. So I've seen a lot of those things. And I think these things are going to continue to be problems because they're human nature, a lot of them.
Right, unless there's some strong, I guess what you're saying is there's sort of an incentive problem, that right now the incentives are still in favor of people minimizing the engagement, of pretending there's no problem because they're not getting called on it. If something bad happens, somehow they're not losing their jobs, or they're able to get away with it. And as a result, this kind of stuff is just going to keep happening. They're not willing to take stronger measures.
I think it's going to diverge more and more. I think there's going to be a subset of people who have had a terrible incident, or their mindset is particularly pro-security for whatever reason. And I think, I don't know if that's the 10% or 20%, but I think they're going to get better, and they're going to be aggressive about it, and they're going to be better in 3 years than they are today. I think the rest are just going to kind of keep their heads down, not try to ruffle the boat, and just kind of coast along and hope that there's no problems. And there may be some problems.
Yeah. Well, I know, so here at Maryland in our cybersecurity center, we have several people that look at sort of the public policy and economics and that sort of angle of things. And it's very challenging, right? I mean, the legislature, for example, has for many years claimed that they want to pass some sort of comprehensive legislation, and they've just never been able to do it because the downsides of restricting what people can do with security just seem to be too high. And yet, since that time, we've had breaches of Home Depot and Target, and had lots and lots of people's personal information be disclosed, which is a drag on the economy. And so I don't know, until things, I guess I agree with you, until things get bad enough, only a certain set of maybe those who are directly affected, I think, are going to be motivated to change. And the question is, when is the sea change going to happen, where people will pay attention to all the work that people like yourself and folks here at our center are trying to do?
Mhm. Yeah, it's hard to know. Yeah, I think it's got to come from the top down. And I think the fact that we are seeing these things in the paper now, whereas we weren't seeing them in the paper 5 years ago. But you've got Target in the paper every day, and Home Depot in the paper, and all these cyber attacks in the paper now. If nothing else, the ignorance or level is falling a little bit, where people no longer think that there's no real threat. So we do have that going for us. Whereas they are willing to take things a little bit more seriously now, and hopefully dig a little deeper and make the changes they have to, because it's not easy. And when we go in and do a penetration test, we tell people, you're not going to be better next month. You're not going to be really better in 6 months. It takes a couple of years to get all the organization and the organization right, to get the network right, to get the software right, to get the processes right. It takes a while. It's a hard problem.
Well, I think that's an excellent note on which to end. So thank you very much for joining me for this interview and for sharing your insights.
All right, no problem. I had a good time.
Great. Okay, so today I'm really happy to have with me Patrice Godefroy, a principal researcher at Microsoft. I'm going to now read a little bit about him, his bio. So he's been at Microsoft in Redmond since 2006, and before that he spent 12 years as a researcher at Bell Labs. There he earned his bachelor's and doctorate, sorry, not there. Before that he earned his bachelor's and doctorate degrees from the University of Liège in Belgium. Patrice is well known for having invented Verisoft, which is the first software model checker for mainstream programming languages like C and C++. And more recently, and something that's going to be a big topic of today's conversation, he co-developed Sage, which is the first white box fuzzer for security testing. And Sage has been credited with having found roughly 1/3 of all of the security vulnerabilities discovered by file fuzzers during the development of Microsoft Windows 7. So Patrice, thanks so much for joining me, and welcome.
Well, thank you very much for having me.
All right, so I'll get right to it. So in this class, the class that I'm teaching on Coursera, we're covering common security problems in software like buffer overflows and SQL injections and format string attacks and things like that. And you've worked on automated means for finding and preventing these problems. So I'm curious, given all of your experience, what's your view on the state of the art? What do these tools do well, and what are they not so good at?
Well, I think yes. So over the last 15 years, there have been a lot of progress on these kind of tools. So automatic program analysis tools, and they are, I would say, two main classes, and I hope you would agree with that. First class is static program analysis, and second is dynamic program analysis. So static program analysis tools, they kind of read the code, usually source code, and then they scan it, and they kind of try to find all kind of issues with the code, like bugs, like those that you just mentioned. And then dynamic program analysis tools, they run the code. So usually they have the one execution of the code, and then do all kind of check during the execution, again, to try to find all kind of like vulnerabilities or bugs. And then you can run them repeatedly, and so you can check multiple execution this way. And I think that really, like for instance, for static program analysis, I mean, it really took off. I think I would say around like 2000, there started to be really commercially available tools inside Microsoft. We have a tool like that called Prefix that started to be developed really in the late 1990s and early 2000, and was deployed really a large scale throughout the company. And these tools have found really lots of issues and helped quite a bit. And they are used routinely really today. And dynamic also tools have been used for quite a while. So runtime checkers like let's say like Purify, Valgrind, App Verifier. Internally, we have a tool called TrueScan. So these tools also find a lot of bugs and memory leaks and performance issues and things like that. And then in the area of security, also starting in the early 2000, I would say around that time, there have been also a lot of work on security testing, also called fuzzing, basically to try to find security vulnerabilities, mostly in parsers for files and packets. And then there have been also a lot of progress over the years in having more sophisticated techniques, finding more bugs using fuzzing. So, I mean, that's kind of a general answer. So there's been a lot of progress, but there's still room for improvement.
Do you at this point, as you say, they've been under development for maybe 15 years. Are there things that these tools are just awesome at? You mentioned they're in routine use.
Yeah.
For what things do people routinely use them versus things that are maybe still somewhere off in the future?
Right. So, so I know a little bit better the area for like systems code, buffer overflows, memory safety. So actually, for like cross-site scripting attacks and like SQL injection bugs, things like that. So I do not know what the ratio of static versus dynamic analysis, but for buffer overflow, memory corruption bugs, etc., both are used extensively. So usually static analysis is used first, earlier, as the code is being written. And now you have variants of these tools that are basically embedded into, in development environment like Visual Studio, and as soon as you type, they can also perhaps flag some errors. And so they are used early on. And so these static analysis tools, usually they are fast, but they can be imprecise. And so, and in contrast, the dynamic analysis tools are used when you can run the code, so after you can compile it, etc., it builds. And so they are run later. And they tend to be more precise, but they only check some execution, typically not all execution of the program. So they're very much complementary, and in practice they are used at different points during the development, software development, and so they are very much complementary. And we're still, as a community or inside Microsoft, also developing these tools further to improve basically this precision and the type of bugs that they can find and reduce the cost of using these tools.
Okay, great. So, so you yourself have worked on these sorts of automated analyses, both stack analysis. So, software model checking in the case of Verisoft, back, and then also since then, white box fuzzing. So, I'm curious, having worked on software model checking for so long, what prompted the switch to working on white box fuzzing, starting with, I believe, Dart, which was a forerunner of Sage?
Right. So so in my mind, so both Verisoft and Dart and white box fuzzing and our tool Sage that implements white box fuzzing, they are all related to this idea of software model checking, where one wants to try to prove, to have to exhaustively test programs. In the case of Verisoft, the main source of non-determinism there was due to concurrency. So the goal was to find concurrency-related bugs. And in the case of Dart or white box fuzzing, the goal is to find bugs in data-driven applications. And so there the non-determinism is due to the large input space for data. But the goal is the same in the sense that in the limits, so if you apply into small example or if you let it go long enough, you get verification. So verification means it's a tool. A verification tool is a tool that can not only find bugs but also prove the absence of bugs or a class of bugs under some assumptions. Or a testing tool is just a tool to find bugs. And so, so myself and many others in the research community have tried to basically develop new tools that are inspired by verification techniques in order to define new bug finding techniques, either static or dynamic, basically, like testing-based, super testing kind of techniques. So the reason for the switch in my case is simply because so when I worked at Bell Labs for 12 years, and there a class of very expensive bugs were inside communication switches, like optical switches or CDMA base station or phone switches. And so there you had most of these bugs were due to concurrency issue, reactivity, real-time issues inside really the core of a switch. And these were like very expensive bugs and very hard to find. And that's why a lot of work initially on motor checking in the industrial labs at least came out of Bell Labs, because there was a strong interest for these type of techniques, which have been proven to find quite subtle and expensive bugs basically in these type of switches. And when I moved to Microsoft in 2006, here at Microsoft, I would say that as a class, the most expensive bugs that Microsoft faces are probably security-related bugs. And so there, it's not concurrency related, it's really bugs that are due to malformed inputs. So for instance, Windows client, so Windows that runs on every laptops running Windows, for instance, etc., or PCs, includes support for about more than 300 file formats. So they have 300 file parsers that are embedded in every laptop running Windows, for instance. And so it's a big attack surface in the sense that if you can craft a specific input file and then open it, process it through the software running on your machine, and you can trigger a buffer overflow. In principle, this could perhaps be exploited, and then you could hijack the execution of the process that runs on your machine. And so this is a big problem for Microsoft. Office is the second big target and big customer that we have for these type of techniques, because Office also supports, depending on how you count, but tens, dozens, maybe a few hundred, depending on how you delimit basically, but parsers and sub-parsers, etc. And both Windows and Office are successful products. They have been deployed on over 1 billion machines. So when we have security-related bugs, they're very visible. We need to patch basically 1 billion machines through like Patch Tuesday kind of bugs, etc. So this is very expensive for Microsoft. Hence the interest of kind of developing and pushing further techniques for finding bugs in this type of application.
So Microsoft, before you got involved with Sage, was using fuzzing technology, and you developed this new approach that was inspired by program analysis to do fuzzing. I wonder if you can characterize maybe the difference between other sorts of fuzzers that Microsoft uses and Sage, and then also maybe the balance of how much time is spent using Sage-style fuzzing today versus maybe before when you got started.
Right. So I would say that there are 3 main types of fuzzing, and they were proposed in that order. So the first type of fuzzing is the simplest one, is so-called black box fuzzing. So it's random testing. So if you have, let's say, for file fuzzing, you have a file parser. So the parser means here just a program that's going to read that file and do something with it. And so the simplest form of fuzzing, and the oldest one and the most basic one and the more used one, is so-called black box fuzzing. So you take, for instance, a well-formed input file in that format, and then you randomly fuzz, you randomly switch the value of bits in that file. And so there are various variants like byte fuzzing, where you took 1 byte, you do 256 values, then you move to the next one, etc. So you can do the fuzzing. So this way you generate a lot of variants, and then you try to open this file, run the program that reads that file with all these variants. So it takes a lot of machine time, and you hope to find a bug this way, like a buffer overflow, for instance. So that's black box fuzzing. The second class of fuzzing techniques, we call them grammar-based fuzzing techniques. So there, in addition, you have a grammar that represents the input format of the input, that's the format that the application you're interested in to fuzz is supposed to take as input. So for instance, you have like Excel or Word or JPEG or GIF or whatever. And so now you have a grammar that basically constrained the fuzzing a bit more. So you can say, well, you can go through production rule of the grammar, and by construction generate basically inputs that are accepted, that are in the language of the grammar. And then you can also enhance grammar-based fuzzing this way by having heuristics. For instance, saying, well, these 4 bytes, they are really meant to be an integer. And then you can say and try more often like specific value like 0, -1, and even associate probabilistic weight to the production rule of the grammar. So basically, when you go traverse and generate inputs, so you can control basically random fuzzing this way. It's a way to guide random fuzzing. and make it much more intelligent thanks to the grammar. So this is also a very popular approach, and the drawback of grammar-based fuzzing is that you need a grammar. And so the grammar-based fuzzing, in some sense, is as good as your grammar to a large extent. And so this has been also used quite a bit, including inside Microsoft. And the third kind of technique, large class of techniques, is what I would call white box fuzzing, which is what we started really developing and here at Microsoft in 2006, roughly speaking. And so there, in white box fuzzing, we run the program. So we have a file parser and a seed file and an input, and then we run the program on that input to see what it does with it. And we do what's called symbolic execution. When the program is running, we also execute that specific execution symbolically, and in this, basically the outcome of that is to see what the program does with its inputs. So we generate constraints that correspond to tests on inputs, and then later on we can negate this constraint to try to use a constraint solver to generate new tests that are going to drive the execution of a program through different code paths. And so we call this white box fuzzing because there the fuzzing is not done offline, but really we have to analyze the program and see what it does with its input. And then the tools suggest different inputs to drive the program through different code paths. That's white box fuzzing. There are various variants, of course, that have been proposed and various levels of cost precision. The advantage, so white box fuzzing is more complex, the tools are more complex, but it's still fully automatic, so you don't need a grammar. And so once you have a tool like that, you press a button and essentially it goes, basically. So, historically, I think black box fuzzing was the first and probably started to be developed and used quite a bit in the early 2000s. Grammar-based fuzzing soon came after, like also between 2000 and 2005 started to be developed. I mean, I'm talking about mainstream kind of fuzzing circles. And then we started with 2006, etc. white box fuzzing. It took us a few years to get traction and get deployed on a large scale. And today we still, actually at Microsoft, we still use the three type of fuzzing techniques in production, with the exception of grammar-based fuzzing, which sometimes we don't have good grammars for some formats. We have so many different formats. Finding the format itself is a hard problem. There have been also attempts to try to automatically generate these grammars and reverse engineering, and sometimes in white box manner. But these are mostly, I think, stayed in research cycles so far. I mean, it's less frequently used. And so grammar-based fuzzing, there are people exchanging grammars on the internet, etc. So for some formats, they are very well covered, and others, they are not covered. And it's labor-intensive. I mean, you need to pay somebody who is going to write for weeks, basically, grammars and guess and try. So this is kind of more expensive than black box fuzzing and white box fuzzing in some sense. The increment cost is higher. But today, we use all three inside Microsoft, usually.
So they're all, I mean, so I take from that that they all are effective in various ways. That for example, I could imagine that in white box fuzzing, you're going to follow, you're driven by the control flow paths of the program, and some control flow paths are they're just hard or difficult to reach. Whereas you might get very lucky when you're doing a black box thing, or maybe you're not so lucky, but because you put the extra effort into writing the grammar, you're able to get sort of deeper into where the program goes, or maybe deeper is the wrong word. You just end up covering different parts of the state space of the program with these different techniques, and so they complement each other.
Yes, I think your intuition is absolutely correct. I mean, this is intuition at the end because we're still trying to figure out what's the really fine print of what technique is good at and what are the threshold, what kind of bugs, etc. But yes, in the end, I think they're still very much complementary. I would love to be able to claim that Sage finds basically everything that other fuzzers can find. And in some cases, I mean, we've done some experiments, etc. But in general, also, the product teams, they don't want to put all their eggs in the same basket, and so they kind of also, if a hacker is going to use black box fuzzer, you want to also use black box fuzzer because that's what they would find basically. And in practice also, so when we run fuzzing, like in large organizations like Windows, the fuzzers don't run exactly on the same code as well, which makes comparison difficult. So for instance, you might first, as a first kind of test, run some like default like by for instance black box fuzzing, because it's offline fuzzing, it's easier. It's easier to kind of test it on like unstable build and things like that. And later on, you can go to the more sophisticated tools that needs to run perhaps for a longer period of time, or and things like that. So it's very much a mixture in the end. But yes, and so absolutely for grammar-based fuzzing, for instance, especially for like very sophisticated languages, I mean, having a good grammar, give you a heck of a head start, basically, to understand what the format is about and how to drive the execution of a program. So in fuzzing in general, we always use seed files, so well-formed inputs that give us also a head start, right? So you can also have combination where you use first a grammar-based fuzzer to generate, let's say, 1,000 seeds that cover the grammar well, and then you use that as a test suite, basically, for white box fuzzing. So we use these kind of techniques as well. I mean, using seed files is also a common practice in the fuzzing world that we also use with white box fuzzing. And so we have also to refresh these seeds, and how to kind of try to have more diversity in this test suite also. And there, grammar-based fuzzing can be used also for that. So
I'm wondering, as you talk about the different tools and the history that Microsoft has had with using these different tools, and also the history of automated analysis, having started with Prefix maybe in the late 90s and it becoming into more common use. Sort of what the story was from your point of view. You come into the research division of Microsoft and you just start to develop this technology, and then you know, what was the step that went from a tool, a prototype that you were developing, to getting to the point that now it's being run on, you know, like you said, Office and Microsoft products that are used all over the world? I imagine that story of getting it adopted is going to mirror at least a little bit of story that maybe people taking the class, if they tried to get tools used at their companies, you know, maybe there were certain roadblocks or whatnot that you encountered that maybe they would encounter as well.
Yes. So we started the development of Sage, which tool that can implement this white box fuzzing approach. And in 2006, in 2007, we had a first prototype, and we were fortunate to have some people in the product group that were really intrigued and interested in this. But at the beginning, we didn't know how successful it would be. And so we started basically applying it to a handful of users, and we found bugs that have been there for a long time and that were missed by everything that was thrown at them so far. So that's kind of was a. And then we had there was the manager, so the person at the head of security testing for Windows Client for Windows 7, who and his name is Eric Douglas, and he was actually an early he kind of was early on suggesting that, encouraging us to do this project. And at some point he decided to so he was at the head of fuzzing actually for Windows 7. And then he decided to invest basically more significantly in Sage, and then it was deployed for the first time on about 2/3 of the file parsers embedded in Windows Client were fuzzed for the first time with Sage in the 2008-2009 timeframe. And it turns out that it's a very effective way of finding bugs, especially on binary parsers. And so, as you mentioned earlier, I mean, at the end, to give you an idea, Sage was credited to have found about 1/3 of all the file fuzzing bugs found during Windows 7. And so, because Sage was also the first, new tool at the time, it was run last, which means that all the bugs found by Sage were missed by virtually everything else, which is black box fuzzing, grammar-based fuzzing when it was applicable, and also static program analysis that was run way earlier. But and maybe, by missed, that maybe the static analysis tool would have flagged that bug, but among a sea of false alarms, and I do not know exactly why, but in the end, the bug was still there when we fuzzed it. So when we run these tests, basically, when the Windows team ran these tests, and so the Windows 7 now was our first basically big customer. We were also lucky that and this is also something that I recommend in some sense for other companies, and this is a trend. Very visible inside Microsoft. There's been a trend of centralizing fuzzing, So in Windows Vista, for instance, which was before Windows 7, the Windows team that was doing fuzzing in a distributed manner. So there may be, let's say, I'm just making this up, but let's say 100 group that need to do some fuzzing. Well, there would be 100 fuzzing guy, and they had to grab some machine and do somehow some fuzzing. Starting in Windows 7 client, they decided to centralize fuzzing. But for me, the tool provider was great because I just needed to talk to that specific team, and I got leverage this way. So there, if you Mike are the head of a development team and I'm in the fuzzing group, what we have to do is you have to identify basically, that's part of the process that we use at Microsoft. There has to be a review at the architectural level for your component, where you have to identify your untrusted interfaces. And then you have to give me some kind of test driver and some seed inputs. But in the centralized fuzzing lab, will run the test, run all kind of fuzzer, do all kind of things, triage the bugs, eliminate duplicates, and then I will send you email. I mean, we'll use bug database kind of thing to communicate, and then I'll send the bugs back to you, basically. And so now you don't have to worry about all this fuzzing business, etc. A bunch of experts are doing it for the entire Windows organization. So at the beginning it was Windows 7, but now Windows 8 moved to the centralized fuzzing. Now we have recently a reorganization where it's operating system groups, including Windows Phone and Xbox, have a single centralized team. And the same trend happened in Office. And so for tool provider, it's great because now I have a few but very smart users. And so for sophisticated tools, it's easier for me to educate a few people than hundreds. Actually, could not do that. Don't have the bandwidth, the time to do that. And then it allows basically more sophisticated analysis to be run as well, because they have a lot of machines available for all kind of, for fuzzing, but also variants basically available.
That's really interesting to hear. So that kind of dovetails into another thing I'm curious about, which is, so you've described an evolution of the development process where people are using static analysis all the time. Of course, they're doing unit testing and code reviews and things like they've always done before. And then they also now are adding this very late phase, right? I mean, this is to the point where these things are building, running, and you can hand them off to a third party to do this fuzz testing with them. I wonder, stepping back and looking 5 or 10 years into the future, seeing how the development process has evolved to the current state, where do you think things are going? What potential is there that's in development that's yet to be exploited? How are things going to get better? Are certain practices going to fall away? Can you look into your crystal ball and imagine what things will look like in 5 years?
Yeah, this is a good and tough question. As Yogi Berra used to say, it's hard to make predictions, especially about the future. But I don't know. But one trend that one sees, and not just here, but all externally, I mean, in the market as well, is perhaps having like program analysis of fuzzing services, where you have basically, so you can kind of, as an individual company, you might outsource a little bit of these analysis techniques. And perhaps, I mean, you still need the expert for but for the techniques, the tools themselves could be running in like a cloud, for instance. And so now you get economies of scale this way, or you can mine basically, I mean, how you can do more sophisticated analysis, for instance, and find like API usage bugs, or I mean, cross-application kind of bugs, and all kind of things like that. So this is definitely a trend going on. And maybe in testing it could also reach that point. It's a little bit, the infrastructure usually a bit more complicated. If you do, for instance, Windows, where some of the stuff is really close to the hardware, so it's hard to, you cannot run this on a standard VM, etc. But for higher level application, I mean, definitely it opens up new possibilities, economies of cost, and also perhaps sometimes running more expensive analysis. Another general research comment, comment about research, or they could also, hopefully, we will continue to see new tools, and especially perhaps trying to combine the strength and of both static and dynamic analysis. The strength of static analysis is fast and can go anywhere kind of things, and always on kind of tools. And in dynamic being precise, very few false alarms, and so that's the strengths of dynamic program analysis. And have more and more of these kinds and package them in a way that it's really usable by either for specific application domain or hopefully for so large classes of users. So these kind of tools becomes more and more mainstream. So overall, I think there's still a lot of software being written, and of course, and it's more than ever impacting society. Security is very critical to many different type of. So there will be more progress. It's hard to crisply define exactly how progress will happen, but I mean, there is a need, so it should happen.
I'm just thinking about this synergy that you were talking about of static versus dynamic analysis. I'm wondering whether, just thinking about the way things have evolved at Microsoft, that so one point of view might be that there are these very simple, complete, very likely to be correct, low false alarm static analyses that can find bugs really fast while you're developing your module. And this is good because you can't run the code yet. It's not part of a complete application. And they find these bugs, and therefore these bugs get eliminated maybe early on. So I imagine this is sort of what's happening now. But then there are more sophisticated static analyses. You were mentioning verification before, that you might be able to prove that your component sort of does the right thing for some specification of the right thing. And then I imagine that will have impact on downstream use of tools, right? So when the more components you develop, say in type-safe languages or using static analysis up front, that creates an opportunity for the tools later on, rather than treating every binary is the same. If this binary came from a outcome of fuzzing, even white box fuzzing might be a little bit different. So I think, as you say, it's hard to look and see how this interplay will evolve over time, but it seems to me that there's an interesting opportunity there.
Absolutely, and there's a whole class of bugs. I mean, a lot of development currently going on in developing apps, for instance, for like smartphones and things like that, or they are like browser kind of application. Unfortunately, this is not really my area of expertise, but there's also the world. These are like sub-worlds, so to speak, and I mean, in the sense, the comments that I made, I think, are applicable to all of them. But maybe I was thinking more about systems code and like buffer overflow kind of things, and like networking software and like file parsers and things like that. And so also. Absolutely. I mean, in the other like application development for like apps for like phones, for instance, etc., or for like the web, and so these are also other very specific kind of markets, so to speak. And so there's also a lot of new tools coming up and different approaches there. And so definitely the world is changing. I mean, if you look at the 5-year time frame, it's changing quickly.
Oh, that's very cool. I wonder, so just to finish up, continuing to look ahead a little bit, maybe a little bit nearer term, can you say a little bit about research problems that you or the community working on these sorts of techniques, symbolic execution or whatever that supports white box fuzzing? What are some of the problems that you're looking to solve today?
Right. So there's a lot of work currently being done in this space, as you know. But so there are two main. I mean, okay, personally, the way I view it is, or a simple way to see what's going on is twofold. So in the short term here, so one problem is to see how far are we from verification. So sometimes we have run Sage, for instance, for a long time now. So actually, we've run Sage now for a total, roughly speaking, to give you an idea, about 500 machine years. So Sage has been running nonstop, on average, about 100 machines over the last 5 years. And today, as far as I know, so it's like the largest computational usage ever for an SMT solver, the satisfiability modular theory solvers. And so, but one thing that's so in some cases we've been running it for a long time, and we don't find bugs anymore. And so now, how far are we from verification? I mean, how can we even improve the techniques, especially the techniques used to deal with path explosion? There's a number of the combinatorial explosion, number of paths that need to be explored in such a way to have complete coverage, even up to some size of inputs, for instance, etc. So that's one. So it is, of course, related to other approach related approach to program verification, like so-called verification condition generation, bounded model checking, etc., which are other techniques basically that try to take programs and have a precise logic representation of those programs, and then you can, using solver, reason very effectively, very efficiently about the possible behaviors of the program. So that's one direction, is what's the gap with verification. The other is try to find, short-term, more application domains. So for instance, SAGE is used mostly today, still today, for file fuzzing. But now what about packets? What about services? What about unit testing of in general, for instance? What about managed code? So we have another project called PEX here, which does unit testing for .NET code, etc. But so how can we get more usage and users for that? And so try to find basically this machinery of using symbolic execution and constraint solver is still very limited to a specific application domain. And so while we're very happy and proud of that success, this is just the tip of an iceberg or scratching the surface. Most developers at Microsoft do not write code for 5 parsers. So how do we reach other application domains on your other communities? How can we maximize the impact of this type of research, not just the work that we do here at Microsoft, but as a community, basically? How can we impact the world further in order to continue doing the research, get our funding, etc., of course, also. But and so there, so like trying to be better at what we do, which is the verification angle, and also trying to make what we can do already more applicable to a larger class of applications and users is another main theme.
Okay, fantastic. Well, I don't have any more questions. Unless you'd like to add, I will say thank you so much for joining us.
Well, thank you very much for having me and giving me an opportunity to talk about this work.
Fantastic. Thank you.